I'm going to give a presentation, and in between the presentation sometimes you'll see exercises pop up. And the intention is that you take pencil and paper and you try to do the exercise in 5 or 10 minutes. These exercises are to help you get a bit finesse with what matrix product states are and bits and pieces of the philosophy behind them. So exercise 1 and 2 are sort of a joke or a little introduction, but starting from exercise 3 you'll get a little bit of time, and maybe if you still need a VSC account, find the guy in the red polo who's now waving. That's Wart. He's tech support.
Everybody does have a Flemish University should comment up to me.
So that's one thing, there are exercises in the presentation. Second thing is I chose to make only a few slides, 55 slides for 2 hours and a half. That means that if you have a question, you are very welcome to interrupt me and to ask it, because most of you probably have no idea what DMRG is. And if I forget to tell something, or if you just have a question, the chance is very high that other people have the same question, so just ask. And if I'm not looking in that direction, maybe you can cough and or wave, or maybe say, Sebastian, I have a question, and then I'll stop and answer. So welcome, and I'm very glad that you all could come during the holidays. As you all know, the presentation consists of 2 parts. There's a morning session, theory session, so with the presentation, with the exercises, and with a lot of questions from you. And then there's an afternoon session, a hands-on session on the Ghent University supercomputer, during which you will make a few exercises with ChemPS2, which is my DMRG code. The presentation consists of 9 parts. First, I'll try to tell you where DMRG fits in the picture of quantum chemistry today. It doesn't mean that what I'm going to tell you is the only good place in quantum chemistry where DMRG can be useful, but it just so happens that today 95% plus of all DMRG calculations in quantum chemistry fall within that corner. In order to introduce DMRG, I'm going to talk about quantum entanglement. The underlying wave function ansatz of DMRG are matrix product states, and I'll introduce them by starting with a full CI wave function and making a few decompositions going towards this specific ansatz so that you'll understand what it looks like. Then once we know the ansatz, I'm going to talk about how you can optimize this ansatz, and that's with the DMRG algorithm. Then I'll discuss various properties, how you can introduce symmetry, and a little introduction to ChemPS2, which is the code we're using this afternoon. And the place where DMRG will be used is as a replacement for full configuration interaction, and the latter occurs in quantum chemistry in the CAS-SCF and CAS-PT2 and MRCI multi-reference methods, and the 2 I'll discuss today are CAS-SCF and CAS-PT2, and when DMRG is used as an exact solver, the names are DMRG SCF and DMRG CAS-PT2. Now I'll just give you the link where you can find the hands-on session for this afternoon. So, first small exercise. Who are these people and what do they have in common?
White Caucasian man.
From Europe. Good one.
They are quantum physicists.
They are quantum physicists, indeed. So you have Max Planck, Niels Bohr, Paul Dirac, Heisenberg, Pauli, and Schrödinger, and they are, quote-unquote, the founding fathers of quantum mechanics, and more specifically many-body quantum mechanics. And one of them has made a quite famous quote, and at least in Dimitri's group, every PhD thesis opens with this quote, and it frames quite well what we are going to talk about today. So we're going to try to read this quote together. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. What he is talking about is many-body quantum mechanics, and more specifically quantum chemistry, and even more specifically non-relativistic quantum chemistry. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. What he's talking about now is the superposition principle of quantum mechanics, and due to the superposition principle, you have the exponential scaling of the Hilbert space with system size. And because of the superposition principle, we all have a job because we all try to find approximate solution methods. And that's the topic he'll talk about next. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic and molecular systems without too much computation. And all that has been done since then is find better solution methods for certain trade-offs of accuracy versus computational time. So just to place this specific approximation in the bigger picture of approximations in quantum chemistry, typically the electrons move much faster than the nuclei, and as a first approximation you can say they move instantaneous, and then you're using the Born-Oppenheimer approximation, so you're solving the electronic Schrödinger equation for fixed nuclei. If you then look at the many-body Schrödinger equation, you have a partial differential equation in many coordinates, and the way to make it workable, two things. You introduce chemical basis sets, so you go from partial differential equations towards algebraic equations, and second, you introduce second quantization in order to keep things tractable. And you don't have to do it, but at least it's quite often done. You can neglect relativity initially and then treat it in perturbation afterwards, but you don't have to. And those three approximations we're going to take as a given today, and the only thing we are going to talk about is approximate solution methods. Okay, so we're going to use chemical basis sets, and these chemical basis sets are Gaussian atomic orbital bases, which you expand around atoms, and then you take linear combinations of these AOs, so atomic orbitals, in order to get the single particle states or molecular orbitals for quantum chemistry. You'll see throughout the presentation the number L quite a few times. That's the number of spatial orbitals. You'll also see the number M quite a few times, and that's the number of electrons in the system. This here is just to illustrate the superposition principle. You need to consider every possible distribution of your electrons over your orbitals, and your wave function is then a particular linear combination. The problem is that these possible distributions, if you have a spin projection zero wave function, it scales as this binomial coefficient squared, and that's faster than polynomial, so you have exponential complexity. And that causes that you are limited to about 16 electrons and 16 orbitals when you want to construct the exact full wave function up to any accuracy you want. You can debate whether it's 14, 14, 18, 18, but at least you're in that ballpark of sizes you can handle. And then people have wondered what they can do in order to circumvent the exponential scaling, so you need to find polynomial solution methods. And what was the first method people invented, which takes correct Fermi statistics into account, and so on and so on. What's the simplest thing you can do in quantum chemistry?
Still early.
Yeah, so this guy is Hartree. So who will those two people be? This is Spock, and who's this then? No Boholiobov, no, you're gonna stick with fixed particle number. So this guy is Slater. And they have invented Hartree-Fock theory or mean field theory. And the idea, hand-wavingly, and throughout the presentation I'm going to only discuss restricted open shell Hartree-Fock, so no unrestricted versions. The idea is you take one of the possible distributions of your electrons over your orbitals. That's a Slater determinant. In a Slater determinant you typically encounter mostly paired electrons. And they reside in the occupied orbitals. Then you also have empty orbitals, those will be called virtual orbitals. And you then just rotate the occupied and the virtual spaces until you minimize the energy. And that gives you the Hartree-Fock solution, which comes under the form of a Slater determinant, and the method is called the Hartree-Fock method. Okay, then you have one possible distribution of your electrons over a particular set of orbitals, which are your Hartree-Fock orbitals. The next thing you can do is you can take several possible distributions, but you don't want to have an exponential amount, so you somehow want to truncate them. And traditionally in quantum chemistry, people have worked with a truncated particle excitation rank, in the sense that people optimize a Slater determinant. They get the Hartree-Fock solution, which is this guy, and then they're going to say, well, we're going to consider up to, for example, 2 particle excitations. So you take here the electron out, you place it in the virtual orbital, and you do the same for the second one. And this then gives you a configuration interaction ansatz. It's also a variational ansatz, and you can freely optimize all these coefficients here. It makes sense when your Hartree-Fock solution is qualitatively correct and when C0, your reference coefficient, is dominant in the sense that it's the largest weight in your optimized wave function. When that's not the case, you typically encounter the situation where multiple Slater determinants become important to grasp the electronic structure even qualitatively. And then you need to look at multi-reference methods. And the multi-reference method we're going to talk about today is the complete active space self-consistent field method. So quickly, whenever you have more than one important Slater determinant, we talk about strong or static correlation, and the idea is then that you take all the important Slater determinants into account, and you first diagonalize your Hamiltonian in this limited amount of Slater determinants. You get an approximate solution, and then you add all other, or at least a large subset of the other distributions afterwards. So you sort of have a two-step algorithm. You diagonalize first, and then you're going to add on a bit of the remaining correlation, and we'll dub that remaining part dynamic correlation. What you'll see in the first step is that if you typically look at any molecule which has somewhat multi-reference character, and you look at, well, what's the difference between all those important determinants? What you typically observe is that, for example, in the core orbitals, the occupation doesn't change. If you look at the virtual orbitals, your occupation also doesn't really change. It's mostly in a very limited subset of orbitals where the occupation changes over these really important determinants to grasp the qualitative structure. And the idea is then, well, let's just take this subset of orbitals and the corresponding electrons, and we dub it the active space. And you have a remaining occupied space, you have the active space, which are all the orbitals for which the occupation changes over the impermanence, and a virtual space. And by dividing the total orbital space in these three subspaces, you can develop a method in the sense that you can build an active space Hamiltonian by taking the Coulomb and exchange contributions of your occupied orbitals into account. And then you just have a small problem which you need to diagonalize in your active space. You can then again, once you have solved the active space problem, rotate the occupied, the active, and the virtual spaces until you minimize the energy. And that's then the complete active space self-consistent field method. When you have done that, you can add the remaining correlation, the dynamic correlation, with perturbation theory, a configuration interaction expansion, multi-reference coupled cluster, and something which has been popping up quite recently by Francesco Evangelista. That's the driven similarity renormalization group. It's a renormalization group for dynamic correlation, and it has, in certain limits, COSPT2 and MRCC incorporated. So it's sort of a bigger framework in which you could place COSPT2 and in which you can place MRCC. In this picture, there's one thing which sometimes breaks down, and that's the assumption that you can solve your Hamiltonian in your active space exactly. And typically, for example, when you have a pi conjugated molecule which becomes very large, or when you have multiple transition metal atoms in your system, the number of orbitals in which the occupation changes typically becomes larger than 16 or larger than 18 or larger than 20, and you cannot use full configuration interaction anymore, and you need to find another method, and we'll use DMRG for that. Okay. So now I'm going to talk in 3 slides about quantum entanglement. It's not strictly necessary that I talk about it to introduce DMRG, but if you know what quantum entanglement is and you know its properties and how it works, you'll understand a lot more about DMRG, so I think it's a nice thing to introduce. Quantum entanglement is a property of 2 things. First of all, you need to have a wave function, and secondly, you need to have a bipartition of your full Hilbert space. So you all know what a wave function is. A bipartition just means that if you have the full Hilbert space, let's say you draw it as a square, you take a pencil and you draw a line, and you have subdivided your full Hilbert space into 2 parts, A and B. I'll call them throughout the next few slides. Typically, they can be anything. So if you really do the exercise and you draw a square, you take a pencil and you draw a line, the states, if you want to find a basis for the left and the right part, it will be a very complicated basis. Most of the time, utterly useless. You can think, just to get a certain frame ready in your mind to think about it, that you have a set of orbitals and you just subdivide the set of orbitals into 2 parts. For example, have 20 orbitals, you take 10 orbitals and 10 orbitals, and then you can construct a basis for each of the 2 parts. You can construct a Fock space for the first 10 orbitals, and then you can construct a Fock space for the second 10 orbitals, and the total Fock space of all 20 orbitals is then just the direct product space of the 2 smaller Fock spaces. So, bipartition of the Hilbert space into 2 subsystems A and B. Think about orbitals. You can construct a basis for A and B. For example, if you work with orbitals, you can construct Fock spaces. Then you can write the wave function, which lives in the total Hilbert space, always as a particular linear combination over all basis states. And MA and MB are the number of states in A and B, respectively, and they are exponentially large in the sense that you're really summing over the full Hilbert space. The Schmidt decomposition is a particular decomposition of your wave function for the given bipartition, and you can find it by taking a similar value decomposition of this coefficient tensor. So you decompose it into U lambda V, where U and V are unitary matrices, and lambda are called the singular values, or within the context of the Schmidt decomposition, they are called the Schmidt values. And they're always chosen non-negative and real. You can then use the unitaries to rotate the many-body basis states of A and of B separately, and then you end up with this expression for the wave function. And now, to state what quantum entanglement is, it's very simple. If this is a product, in the sense that you don't really have a summation, you just have one value of lambda which is non-zero, then the wave function is factorizable. It's just alpha A times alpha B. And we say that the wave function is unentangled with respect to the bipartition into A and B. If there is a real summation, or there is more than one lambda alpha non-zero, there is entanglement in the wave function with respect to the bipartition into A and B. Very simple definition of entanglement. The question is now, can you quantify it in the sense that if you have two lambdas which are non-zero, you have at least conceptually the idea that the wave function is less entangled than if you have a million lambda values different from zero. Yes?
Maybe you're going to mention it, but can you please remind me why all the singular values have to be positive?
Convention.
So you put the phase in the state then?
You put the phase in the state. It doesn't have to be, because in what follows next, I'll take the square of these lambda values, and if you would do it complex valued, you would actually have the lambda complex conjugate times the lambda, but it doesn't really matter. I indeed put all the phases in the states. Also, almost no one does complex valued quantum chemistry calculations, so...
yeah, maybe the sign can matter, positive or negative.
No, it's only the magnitude of the lambda value which is really important. So before I talk about a quantitative measure to talk about entanglement, I'm only going to introduce one particular measure. It's going to be called the von Neumann entropy. And just like in linear algebra, when you want to talk about a norm, you have the one norm, the two norm, the infinity norm, and in fact any number you can associate a norm with. It's only one particular measure I'll talk about. So there is also an infinity of measures, but it's the most common measure of the amount of entanglement. Just in the sense that when you're just talking about norm in linear algebra, everyone is talking about two norm and not the infinity norm, let's say. So given your bipartition into A and B, and given your wave function, which you then can write in its Schmidt decomposition, you can define the von Neumann entanglement entropy as such. You have these values lambda alpha, you square them, so phase doesn't matter, it's only the magnitude. You have this particular expression, value squared times logarithm of value squared. You sum over all of them and you have a minus sign. Why is the minus sign? If you have a normalized wave function, all these lambda alpha values have to lie in between 0 and 1. If you would then take the logarithm, it will be negative, so the minus sign is just to get a positive number. And the idea is well, it's not the idea, it's if you take many examples and you think about how many lambda values are important and what's the distribution of the different lambda values, you can hand-wavingly say there is more entanglement when this von Neumann entanglement entropy is larger. So for example, we've said that when you have a product state, when the wave function is factorizable, you just have wave function is alpha A, alpha B. Then you have 1 lambda alpha, which is equal to 1 when you fill it in. You just have entanglement entropy is 0. There is no entanglement. And as it becomes larger, this measure, there's more and more entanglement. So first actual exercise. I'm going to let you calculate the von Neumann entanglement entropy for one particular system with 2 bipartitions. The system is the hydrogen dimer, so H2, in a minimal basis, and we're going to look at the restricted Hartree-Fock solution. So I've told you know what the wave function is, restricted Hartree-Fock for H2 in a minimal basis. And we're going to consider 2 possible bipartitions. We're going to first look at localized orbitals. So in the traditional picture where you have one orbital on one atom and then another orbital on the other atom, and you can assume that they are orthonormal, these single particle states. And then, second line, for a different bipartition of the system, you again have 2 orbitals, but you're now going to consider the bonding and the anti-bonding molecular orbital. So I'll give you 10 minutes, and if you don't have a PSC account, talk to what? Okay, so 2 or 3 people have already found a solution. I'll talk you through. So you start by just taking localized orbitals. I've called them phi left and phi right. And you assume them to be orthonormal. If they are not, just pre-orthogonalize them, and then it's fine. And you can define bonding and anti-bonding molecular orbitals by taking the appropriate linear combinations. Your restricted Hartree-Fock solution is then just given by your bonding molecular orbital, which is doubly occupied. You can then substitute your second quantized operators in the localized picture, and you get this expression. And then the question is, well, when you look at this particular formula, where do the lambdas appear? And the answer is, up to sine, you can just look at the possible occupations, because in both the molecular orbital picture and the localized orbital picture, you have 4 possible determinants. You can have, for example, the bonding molecular orbital, which is doubly occupied, and the anti-bonding one, which is 0. You can have 1 electron in the bonding, 1 electron in the anti-bonding, with the spin projection flip, and you can have no electrons in the bonding one, and 2 electrons in the anti-bonding one. Well, if you look at the Hartree-Fock solution, you'll see that there's only 1 of the possible occupations appearing, namely the bonding molecular orbital, which is doubly occupied, and it has a prefactor of 1. The logarithm of 1 squared, which is also 1, so the logarithm of 1 is 0, so you end up with a von Neumann entropy of 0. In the localized orbital picture, you again have the situation where you have 4 possible determinants. Both electrons can reside in the left orbital, both orbitals can reside in the right orbital, or you can have one up electron left, one down electron right, or vice versa. And when you look at this picture without the signs, you see that each of them appears, and each of them appears with a prefactor 1/2. You then need to square these values, so you have 1/4. And then when you fill in the formula, you have minus 4 times, because you have the sum, 1/4, so you just have -1 up to now. And then you have the logarithm of 1/4, minus the logarithm of 1/4 is the logarithm of 4. And that gives you then the answer here. So I've given this particular exercise for 2 reasons. You'll need to play a little bit with second quantization, at least in the beginning of the presentation. And second reason is the amount of entanglement depends not only on your wave function, but also on the particular bipartition which you choose. And for DMRG, later on, it's important in the sense that when you rotate your active space orbitals, let's say from pseudo-canonical to localized, it can really matter. Because if you make a bipartition, the partitioning of the orbital set into 2 parts, in one case you can have a large amount of entanglement, while in another case you can have a small amount of entanglement. But I'll talk about it later. Okay, so now in the next couple of slides I'm going to talk about the ansatz for DMRG, which is the matrix product state. And I'll start with the full configuration interaction solution, perhaps in a form which you're not entirely used to. This here is the actual vacuum, so there are no electrons. And you have a particular set of spatial orbitals which you consider. And these spatial orbitals have 4 possible occupations. They can be empty, there can be an up electron, there can be a down electron, or there can be 2 electrons, an up and a down electron. Well, for each of these cases, so for example, orbital 1, up electron, orbital 1, down electron, orbital 2, up electron, orbital 2, down electron, you're gonna state with this exponent whether it's occupied or empty, in the sense that these exponents can be 0 or 1 and no other values. So this particular summation means take all possible values of all these exponents and let them be 0 or 1. Now you'll say when you do that, you consider the entire Fock space and you don't consider particle number. That's true. The way you consider particle number is if you want to have a certain amount of electrons in your L spatial orbital system, you just say, well, whenever the sum of these exponents in this coefficient tensor doesn't match my desired electron number, these coefficients are 0. So particle number you restrict here in this coefficient tensor. And then, of course, the full CI coefficients, which correspond to a particular occupation of your orbitals, are also given by this coefficient tensor. This here is the occupation number representation of the Fock space. So you just say for each and every orbital whether it's occupied, spin orbital, but the orbitals are restricted in the sense that the alpha orbital is the same as the beta orbital. So for each possible spin orbital, you state whether it's occupied or empty. And in this notation here, you automatically have the correct anti-symmetry, because this right part here equals this cat. In what follows, I won't talk about this right-hand side anymore. It's implicitly assumed, and I'll only talk about its coefficient matrix or coefficient tensor. But of course, you need to think that the cat here is present. Okay. So now we're going to do something, and at first we won't make any approximations. So you have this particular coefficient tensor, and for each orbital you have two numbers. For example, for orbital 1 you have n1 up, n1 down, and we write them here. n1 up, n1 down, n2 up, n2 down, etc. And you have vertical lines and circles. These circles throughout the presentation will denote your spatial orbitals. Your vertical lines will denote the occupations of these spatial orbitals. And you also have horizontal lines. Here you have a thin line, and here you have an increasingly thicker line towards the center. This will be called your auxiliary or virtual or bond index. And it's just a particular decomposition of this tensor into other tensors. And except for the left one and the right one, each of these tensors has three legs. You have a vertical leg, which is your occupation, and you have a left leg and a right leg. And the left leg and the right leg are used to connect with the neighbors. So for example, this guy here is this guy here, and you have alpha 2, alpha 3. The left one also has alpha 2, and you implicitly sum over this auxiliary index, and it's just a particular decomposition which gives you exactly the same values as here. Now, the way you need to think about it is you want to know a full CI coefficient, and you give me a set of occupations. So you're going to say the first orbital has an up electron, the second orbital is doubly occupied, and once I know the full occupation, all these upper indices are known, so all these vertical legs are fixed, and then all I need to do to get your full CI coefficient is to multiply a set of matrices. So the boldface notation just denotes matrices, and that's also where the name comes from, matrix product states. There's now one thing which I haven't. Yes, Steen?
Yeah, so I see that here the circles are the orbitals, but you could also choose to take spin orbitals. So that
yes.
while, is there a specific reason why? Is it just a matter of flavor, or is there really?
I'm going to give the answer now, and I'm going to give it again a little while later. So you can indeed just use spin orbitals. That means that you would have double the amount of circles, and each vertical leg would just have one of the two occupation numbers. The reason why I talk about it in this way is because I'm going to briefly mention spin adaptation. Okay. And for that you need to work with restricted orbitals, and you need to combine them. That's one answer. The second answer, in a more general sense, is that you're gonna do something messy in order to get a polynomially scaling algorithm. In the sense that you have this nice object with good transformation properties, and you're gonna tear it apart.
Where are you pointing?
At the actual full CI coefficient tensor. So you have this nice object with nice transformation properties, and you're going to pull it apart. You're going to pull the first orbital out of it, creating an auxiliary index. Then you're going to pull the second orbital out of it. You're going to introduce a new auxiliary index. And all these auxiliary indices are in fact messy. You don't need them. You only want to represent this guy, remember? But in a second, I'll talk about bond dimension truncation, and then the whole thing gets going. But if you want to use the DMRG algorithm, computationally, you're going to have objects which scale as your auxiliary index times that auxiliary index times the dimension of your occupation or your physical index. And the larger your physical index is, the larger the object is.
Okay.
So you want to keep it small. You could, for example, say, well, I'm going to create a matrix product state with one physical index, and that would then be your full CI tensor.
But if you use, but if you, I'm a little confused now. If you use spin orbitals, then the dimension of each orbital is going to be 2 instead of 4, so it's going to be smaller. So that
Yes. If you want to...
goes against your argument.
So I haven't come to my second argument.
Okay.
So first of all, if you group more and more orbitals together, there's a negative aspect to it, in the sense that your physical index becomes larger and the object which you need to handle becomes larger, exponentially larger, if you group more and more orbitals together. So that's a bad thing. There's, however, a good aspect to it, in the sense that you're going to treat all single particle states which are grouped together in one physical index as exactly correlated. So if you're going to tear things more and more apart, the chance that they'll be properly correlated is smaller. But that'll become clear when I...
The spin symmetry of the Hamiltonian, is that... So would it be... Maybe thinking about your code. If you would use spin orbitals instead of orbitals, stuff would get a lot more complicated, or computationally, mathematically easier, but computational penalties there? Or?
So you can basically forget spin adaptation, because you need to rotate your second quantized operators into spin-reduced ones, and you actually need to do the explicit doublet. So you can forget about spin adaptation if you don't join the alpha and beta electrons which correspond together.
Yeah.
I mean, I'm not saying that it's impossible, it will just be a big mess. And
it's just a bigger mess if you explicitly consider spin.
Yeah. So just to say one thing more about it, one of the explicit ideas in the very first paper of Stephen White on DMRG for quantum chemistry is, next to take care of which orbitals you choose and the standard stuff we've all been studying today, is in fact, well, let's group more than one spatial orbital into one physical index and see what it brings. And the very short answer to that is it has in fact been done. Someone in Garnett's group, Sandeep Sharma, has studied exact D infinity H symmetry, and the non-abelian irreducible representations of that group require to take two spatial orbitals and take them together. So you have one rotating like this and one rotating like that, and you need to join them together. And you can only do it by forming 16-dimensional local Hilbert spaces.
16.
But it's, I mean...
Yeah, okay, I get it.
It's maybe a little bit technical at this point. So the last thing I want to say about this slide is you have this full CI coefficient tensor. You can tear it apart into little tensors which have either 3 or 2 legs. And this is the graphical notation to represent it. And if you want to do it exactly, in the sense that you want to represent any tensor here, then the dimension of these auxiliary indices needs to grow exponentially towards the middle of your decomposition. So in formula form, the dimension of alpha I is the minimum of 4 to the power I, 4 to the power L minus I. Given this pitch, it of course gives you a very nice way to make an approximation, in the sense that my exponential scaling of my problem is here. So let's just remove this exponential scaling, then we'll end up with a polynomial algorithm. That's what we want. And you just truncate the dimension of the virtual bond or auxiliary dimension, and we call it capital D. And that way you have made an approximation, but things, memory, CPU time, etc., scale polynomially, and that's something we've all been craving for. Okay. Before I let you make a couple of exercises, I'm going to talk about one additional aspect, and that's I've introduced matrix product states based on the full CI coefficient tensor. And that's one viewpoint which is somewhat more traditional in the quantum chemistry sense, because you have an ansatz, and then now we're going to talk about, well, not now, but after you've done a couple of exercises, we're going to talk about how you can variationally optimize this ansatz. It's not a traditional point of view of DMRG. The traditional point of view is a renormalization group flow for subspaces of the Hilbert space. And that's the idea I'm going to try to pitch in this slide. If you don't want to listen, don't listen. But so we have L spatial orbitals. Each orbital can be occupied in 4 ways. It can be empty, there can be an alpha electron, there can be a beta electron, or it can be doubly occupied. And if you take the direct product space of all possible orbital occupations, you arrive at the full Fock space if you take correct antisymmetry into account. Now let's just, for the sake of argument, assume that the bond dimension is 20. And you take the first orbital. It has 4 possible occupations. Fine. If you add a second orbital, the first one has 4 possible occupations, the second one has 4 possible occupations, so together they have 16 possible occupations. Now if you add a third orbital, it again has on its own 4 possible occupations, but the 3 orbitals together have 64 possible occupations. 64 is larger than this value 20. So what you're now going to do in your matrix product state is these 64 possible occupations for your first 3 orbitals, they form a basis for the Fock space of the first 3 orbitals. You are now going to rotate these 64 states to another 64 states. That's just a basis transformation. You can always do that. And then of the rotated 64 basis states, you are only going to keep 20. You're going to say about 44, they are not important, and I'm going to discard them. And that's the conceptual idea behind the renormalization group flow, because now you have gone from 3 orbitals with 64 many-body basis states to 20 many-body basis states, and you can add the 4th orbital. The 4th orbital again has 4 possible occupations. The direct product space with the 20 basis states which you have kept is 20 times 4 is 80. This 80 is again larger than the 20 which you want to keep. So you're again going to rotate these 80 many-body basis states to 80 other many-body basis states, and of these rotated states you're only going to keep 20. And you're going to do that further and further and further until you reach the end of your chain. Okay. So now is a good time. There will be 3 exercises right after each other. So if you want to run to the bathroom, if you want to take a drink, or if you want to talk to Wart, now is a good time. I'll run around. In the meantime, you can start by thinking about the first exercise, and that's say you have a restricted Hartree-Fock solution or a restricted open shell Hartree-Fock solution. You get a set of Hartree-Fock orbitals which are occupied and a set which are unoccupied. The question is, if you use those specific orbitals to express your full CI wave function and your matrix product state in, what is the bond dimension, the minimal bond dimension required to express the restricted open shell Hartree-Fock solution in the corresponding orbital basis? Okay, who has an idea? It's indeed 1, and it's very simple to understand conceptually. Why? If you have a Hartree-Fock solution, the Hartree-Fock orbitals all have a definite occupation, in the sense that if you point towards one of the occupied orbitals, you'll say that orbital is occupied with 100% certainty, independent of the occupation of the other orbitals, because you're considering the Hartree-Fock solution. And because the occupation of each and every orbital is independent from the occupations from the other orbitals, you can factorize your full CI coefficient tensor. You can just factorize it, because you can state, well, if my Lth orbital is always doubly occupied, if I fill in 1, 1 here, I get a 1 back. If I fill in 0, 1, 1, 0, or 0, 0, I get a 0 back. And my full CI coefficient for the Hartree-Fock solution is 0. So the graphical representation of my full CI coefficient tensor factorizes is as follows, which means that you have a virtual or bond dimension of 1. It just means that all your orbitals are in fact uncorrelated. There is no correlation between the occupation of orbital 1 and the occupation of orbital 2. The next exercise, if you have a matrix product state with a certain bond dimension, it's somewhat logical that if you go to a larger bond dimension, that the matrix, that the ansatz space with the larger bond dimension can always capture the wave function with the smaller bond dimension. And I'm now asking you to try with pencil and paper to write down the matrix product state with bond dimension d plus 1, which in fact represents a matrix product state with the bond dimension 1 smaller. So you can assume that you have a matrix product state with bond dimension d, and you're now going to rewrite it as a matrix product state with a larger bond dimension. And then once you have done this, try to draw a Venn diagram relating the full Hilbert space, the matrix product state ansatz with bond dimension d, and the matrix product state ansatz with bond dimension d plus 1. And the orbitals in the whole story stay the same, so you don't change single particle basis when you go from d to d plus 1. Okay. So part 1 of the solution, we're going to consider, for the sake of argument, one particular orbital and one corresponding occupation of that orbital. And as said in the beginning when I introduced matrix product states, when you give me a certain orbital and a certain occupation, I give you back a matrix. And if you want to know the full CI coefficient, you just need to have the corresponding matrix of each and every orbital, and you multiply everything together. So if you now take that corresponding matrix and you stack it with an extra row of zeros and an extra column of zeros, and you do that for each and every orbital and each and every occupation, then if you give me a set of occupation numbers, and I just take all the relevant matrices and I would want to multiply them together, these zeros fall away because they appear in each and every matrix for every orbital. So I see some people looking quite questioning. So the idea of matrix product states is you have a FOCI coefficient tensor and you tear it apart and say you want to know a certain FOCI coefficient, then you give me for each and every orbital the occupations. I just fill them in here and then I fix the physical index and then I get a set of matrices. So I have actually here a vector and there a vector and in between a set of matrices. And then I get the corresponding FOCI coefficient by multiplying all these matrices together. Now, if you just, for all possible occupations, add an extra row and an extra column of zeros in these matrices, they just fall away when you multiply them. Then the Venn diagram. If you look at the full Hilbert space, your matrix product state with bond dimension D occupies a certain corner, and if you go to a larger bond dimension, you occupy a larger corner, which also encompasses the previously smaller corner. That is in fact a nice property because it means that you at least can systematically improve your matrix product state by going to larger and larger bond dimensions. That's of course assuming, I'm just going to finish my sentence, that's of course assuming that you stay with the same single particle basis as you increase your virtual dimension.
And my question is about the change in D. Is there any criteria on what coefficients are taken out, or it's just the last rows and columns of the matrix? Or
so about the actual optimization of these tensors, I'm going to talk in a second. Okay. If you increase, you typically do it. So I'll answer your question explicitly when I get there. That'll be the easiest. Any other questions? Then the last but one exercise. If you have one matrix product state which represents one wave function and you have another matrix product state which represents another wave function, you can take a particular linear combination of both and they will also represent a wave function if you take proper normalization into account. The question is now, if you add or take a linear combination of two matrix product states, how can you get it back into matrix product state form? And the answer is actually surprisingly close to the previous exercise. And if you get that as well, then I think that you know everything about matrix product states that you need to know. Okay, so I see a couple of people already have the right answer. I've said in the previous exercise here that the whole idea of matrix product states is you give me the orbital occupations, I fetch all the matrices and I multiply them together, and this then gives me the required FOCI coefficient. Now when you add two wave functions, you just want to have for a certain set of occupations, the sum of the FOCI coefficients. So the way you can obtain it with matrix product states is again by adding a sufficient amount of zeros, but in fact by making sure that if you multiply the matrices, they only will talk to each other in the end when you take the sum. So let's say you start at the left and you multiply the matrix chain, you add zeros here and here, they will multiply independently. And only when you close at the right hand side, you construct the actual sum of the full CI coefficients. And as said before, you need to, of course, use the same set of spatial orbitals and ordering to get anything sensible. Okay. One last thing before I'll talk about the actual DMRG algorithm. This bond dimension, how can you interpret it? Well, I already gave a partial answer in the sense that if you have a bond dimension of 20 and you have 3 orbitals which can have 64 possible occupations, you perform a rotation on this basis to 64 other many-body basis states and you keep 20. So the bond dimension is sort of a renormalized many-body basis. Another way you can think about this bond dimension is as a communication channel between the orbitals, and because they are allowed to talk, they can be correlated, and the more they can talk, the more they can be correlated. So if you truncate the bond dimension, here these 2 orbitals can talk well because you have a good communication channel. Here they can talk less, so they will typically be less correlated. That then has an important consequence in the sense that how you choose your orbitals and how you order your orbitals will become very important in DMRG. That's also related to the Schmidt decomposition and the von Neumann entropy you try to calculate for the hydrogen dimer. Remember that your entanglement was different in the localized orbital basis and in the molecular orbital basis for the Hartree-Fock wave function. In the same sense, your entanglement will, or the bond dimension you need here, will depend on the choice of single particle states, on the choice of spatial orbitals, and how you will order them. Then the DMRG algorithm. How will we optimize the matrix product state? It's a local optimization algorithm where you sweep through the chain, and during each local optimization step you take 2 matrix product state tensors, you multiply them together, and so that just means you contract over this particular auxiliary index and you have a 2-side object. Now you keep all other MPS tensors fixed and you optimize this 2-side object towards the particular wave function you want. For example, you variationally optimize it towards the ground state if you want the ground state. Then you have a set of new numbers here. On this set of new numbers, you're going to perform a singular value decomposition, a Schmidt decomposition in fact, and this gives you 2 new matrix product state tensors and a tick bond, in the sense that if this would be in the center and you would have a bond dimension of D here and a bond dimension of D here, then the tick line would be of size 4 times D. So you have a tick line, and of the Schmidt values or the singular values, you keep the largest one, the D largest one, and the rest you discard. And then you end up again with the same ansatz, but where the numbers in these 2 tensors here have changed and all other numbers have stayed the same. Now I'm going to give you the same, exactly the same talk, but without the figure. So you have two neighboring MPS tensors, sites I plus 1, and you optimize those and all other ones are fixed. You multiply them together, so you contract over the common auxiliary index to form a two-side object, and then you optimize this two-side object towards the wave function you want. For example, if you want to calculate the ground state, you're just gonna find this tensor so that it minimizes the energy. You can write down your typical energy Lagrangian, so Hamiltonian sandwiched between the wave function and minus E overlap. Then you can vary with respect to the complex conjugate of your coefficients you're trying to optimize, and this gives you a linear generalized eigenvalue problem. Linear in the sense that if you would work out the equations, you would actually get a quadratic form in the elements of B here, and generalized in the sense that you have an overlap matrix. Now, on the next slide, I'll talk about gauge freedom, and gauge freedom can be used to remove this overlap matrix so that you in fact have the equation H effective times B equals B times E. So instead of a generalized eigenvalue problem, you in fact need to solve a standard eigenvalue problem. You solve it, you find the one with the smallest energy, and then you have the solution, and you decompose this object with a singular value decomposition. So you have a left unitary object, a right unitary object, and a set of singular values. If the wave function is normalized, the sum of the squares of these singular values equals to 1. Typically, the sum over k will be larger than the bond dimension you want to keep. So you're just going to truncate the summation to the d largest Schmidt values. And it's really the d largest Schmidt values of the bipartition of your orbital space in a left half and a right half, in the sense of the entanglement I've talked in the beginning. Then of course you throw out some of the lambda k's which are small, and if you take the sum of the squares of the ones which you throw out, we call it the discarded weight. It gives you a measure for how much information you throw out of your wave function. Okay. The gauge freedom, as promised. So in Slater determinants, the gauge freedom consists of occupied orbital rotations and virtual orbital rotations, because if you rotate occupied orbitals with occupied orbitals, the numbers you have in your wave function, in your Hartree-Fock ansatz, they change, but the actual wave function, the physical thing it represents, stays the same. The same thing in the Hartree-Fock wave function. If you rotate virtual orbitals with other virtual orbitals, it doesn't matter. Your numbers in the thing you have in your computer might change, but the actual physical wave function it represents stays the same. And it are only occupied virtual orbital rotations which give you a physical change of your wave function. And the gauge freedom are then those two occupied, and the virtual rotations. Of course, you almost never encounter them in calculations because you're used to having orbital energies, and that's a fix of your gauge freedom. You're going to choose those occupied orbitals and those virtual orbitals which diagonalize your Fock matrix. You have also gauge freedom in matrix product state, in the sense that if you have two neighboring matrix product state tensors which have one common index, you can multiply with a matrix and its inverse. And now I say you multiply with a matrix and its inverse, that means that this here represents 4 matrices because you have 4 possible occupations, and for each of those 4 possible occupations you multiply with the same matrix G, and here for the 4 possible occupations you also multiply with the same matrix G minus 1. And because you have G minus 1, it just drops out as the identity, and you have the same physical wave function, which is represented by a different set of numbers. And this is the gauge freedom in a matrix product state. And if you read a paper for which I will give the references towards the end, you'll see how it is used to turn the generalized eigenvalue problem for the local optimization into a standard eigenvalue problem. So how does it now fit in the bigger picture? You take 2 MPS side tensors, you contract, you get a 2-side object, you variationally optimize, you decompose, you keep the largest Schmidt values, you throw out the rest, and you end up with an object with the same form as before. And then you're going to move to the next 2, and you're going to do the same thing. And then you're going to move to the next 2, and you're going to do the same thing. And that way you sweep back and forth, optimizing all the MPS side tensors. And there are a couple of questions which remain to be answered. First one, how do you start? The answer is, well, there are many possibilities. Some people start from the Hartree-Fock solution, from CISD, from a cos-SCF wave function in a small subspace. I just start from noise. The clue is that you, in the end, want to go to a large bond dimension, but that in the beginning, because you're far from the wave function you want to be, you want to start with a small bond dimension. In the algorithm, you'll do a lot of matrix-matrix multiplications, and matrix-matrix multiplications have a computational cost of linear dimension cube. So if you start off with a bond dimension of 100 or 500 versus a bond dimension of 2000 or 5000, if you have a factor of 10 difference in linear dimension in your matrix product state and your computational cost, it's 10 cube or 1000 times as costly. So the clue is just, if you start with the DMRG calculation, start with a small bond dimension, and then you need many iterations, for example, to optimize this 2-side object, but it doesn't really matter because it goes tremendously fast compared to the calculations you'll perform for the largest bond dimensions. And then, once you have optimized and sweep back and forth, and somewhat converge the wave function for a small bond dimension, you go to a larger bond dimension. And sometimes you can get stuck in local minima, and there are 2 things you can do in order to fix it. You can play a little bit with your orbital choice and ordering, and you can add noise in the 2-side object just before you perform the singular value decomposition on the 2-side object. Okay. How does the effective Hamiltonian equation look? So you have a Hamiltonian which acts on something which represents your wave function, and computationally wise, it is in fact a sum over number of orbital squared terms, where you perform a left and a right multiplication with some other form of matrix. And you get this number of orbitals squared, by using so-called complementary renormalized operators. So when you act with terms of the Hamiltonian on your matrix product state and say you want to optimize these 2 side tensors, you have second quantized operators which act on some of your physical indices. Let's say this one and this one and this one and this one. What you then need to do to construct complementary renormalized operators is act with the second quantized operators, close again with a part of your bra, and multiply in the two electron integrals. If you don't do that, your algorithm will scale 2 orders of magnitude in L larger. If you do it properly, applying your corresponding part of the effective Hamiltonian just boils down to summing over 2 orbital indices instead of summing over 4 orbital indices and still needing to multiply with the 2 electron integrals. And if you do it properly, your algorithm has a scaling per sweep which goes as L to the 4th d squared plus L cubed d cubed in CPU time. This one comes from the construction of the complementary renormalized operators, and this one, d cubed, comes from matrix-matrix multiplications. You need to keep matrices in memory and in disk, and the amount you need to keep on disk is an order of magnitude in the orbitals larger. So, how does what are typical values you use in the DMRG calculation? I'm going to talk about the bond dimension, energy convergence, maximum number of sweeps, and the noise prefactor, and then towards the end of the presentation I'll also talk about the Davidson residual norm tolerance. But for now there are only those 4 parameters. As said, you start with a small bond dimension and then you stepwise increase it, and you sweep back and forth until you reach a certain energy convergence or a certain maximum amount of sweeps. And in the beginning you add some noise in order to avoid getting stuck in local minima. Then I also have a second part here where you decrease the bond dimension again without noise. And this is for extrapolation. That's something which I'll talk about in the properties in a second. This noise prefactor, in my code, it's just defined that the noise which is added is bounded by this value. This is the maximal discarded weight which you encountered during the previous sweep. And then you multiply it by a factor 1/2 and this prefactor, and this is the bound of the noise which is added. Why is it this funny thing? If you throw out a small, so if the Schmidt values which you throw out are very, very small, it means that your wave function is quite well converged, and you don't want to screw up the convergence by adding a large amount of noise. So you somehow want to scale your noise with the amount of discarded weight, or you want to scale your noise inversely with the accuracy which you already have achieved. Okay, now I'm going to talk about a couple of properties of the DMRG algorithm. As said, you can use the backward sweep, in which you decrease the virtual dimension again without noise in order to perform an extrapolation of the energy with discarded weight. First of all, you have an ansatz, a matrix product state. And any energy you encounter in DMRG is therefore variational. It's always an upper bound for the true ground state energy. You've done the exercise. As you grow the bond dimension, your energy will go down because your previous solution with a smaller bond dimension can always also be written as a matrix product state with a larger bond dimension. So you can only ever get a better and better and better wave function. And it turns out that in addition to a decreasing variational energy, also your discarded weight decreases. One can now prove that when your discarded weight is reasonably small, your energy is up to first order, a linear function in the discarded weight. That's always true when your first order doesn't fall away, but anyway, your energy is a linear function of the discarded weight. So that allows you to do an extrapolation. And I'm just going to go back 2 slides again. So here you see virtual dimension increasing and then virtual dimension decreasing. What you observe here is your virtual dimension decreasing, so the second half. And the way you approach it with the crank up of your bump dimension is you start somewhere, actually there, but you start somewhere here, and you increase with noise your virtual dimension, let's say 500, 1,000, up and so on and so on, and then you have, let's say, 2,500 with noise, then you go to 2,500 without noise, and then you go back without noise, and you have lower variational energies than you had before. Because you circumvented both your noise and the possible local minima which you could be stuck in. So this example is for the nitrogen dimer, the double zeta bases near equilibrium, but that's not really important. Second thing which you really need to know about the DMRG algorithm is how you need to think about it in a very conceptual sense. If you have Hartree-Fock theory and post-Hartree-Fock methods, the way they circumvent the exponential complexity is by truncating in a manner the particle excitation rank. For example, configuration interaction with singles and doubles. You have the Hartree-Fock solution, single particle excitations, double particle excitations, but no higher particle excitations. So the particle rank is truncated. You give each of the determinants a coefficient, and you variationally optimize all these coefficients independently. DMRG is sort of the dual picture, in the sense that you have this ansatz where you go from a large auxiliary or virtual dimension to a smaller one. If you just fill in numbers, you just take random numbers and you fill them in this ansatz, it will be very unlikely that you'll get a full CI coefficient which is 0. That means that you allow particle excitations of any rank. But the way you decrease the amount of information, or you decrease or you circumvent your exponential complexity, is by correlating the different excitations. That's the meaning of going from the thick lines to the thin lines. They are not independent, the coefficients you allow in your full CI solution, they are correlated.
Is there a visible picture, Sebastian? Like in the particle Hall excitation sector, you can kind of, you can see it immediately, but is it like the feel of what states are kept in the DMRG algorithm and which ones are discarded, or?
So in a
like couple of dots, for instance, you can see what kind of excitations go in easily, but here.
So the excitation picture, okay.
So here you discard states, but is there kind of a feel that which ones are discarded?
No, the very short answer is it are the most. So you do a local optimization, you go back and forth, and say you have a fairly good optimized matrix product state, and then you do the local optimization and you perform the singular value decomposition, and you look at the singular values which you discard or the ones which you keep. So the ones which you keep are the ones which are most probable to occur in one of the two subsystems for the given bipartition. So anything else than that I cannot say. So if you have the wave function and you have the bipartition into a left orbital space and a right orbital space, then you have the set of Schmidt values, and if you perform a measurement, for example, in the left subspace of in your in your wave function and you measure only in the left half, then some of the measurements can occur with a high probability and some occur with a lower probability. The probability of occurrence is proportional to the square of these Schmidt numbers, but there's no physical meaning. I can talk about separately, not now, but about excitation content on top of DMRG, but in a manifold kind of way. But that's an entirely different story from the one today. Size consistency, yes.
Just also related to the previous slide. And that means that changing D affects equally all the correlation between pairs of orbitals, or it can affect differently. So for instance, this in this picture of going from thick lines to thin lines, the thinness is affected equally between all pairs of orbitals, not necessarily.
No, so orbitals.
So okay, this discarding these coefficients, it's made based on the value of those coefficients and not applied systematically between all.
Yes.
Okay.
So if your question was, is it dynamically chosen? The answer is yes. But related to what you said earlier, it is not equal among all orbitals in the sense that if these two orbitals want to talk, so I'm going to talk about, so whenever I talk about talking orbitals, I mean of how much they can be correlated. So if you want to correlate these two orbitals, well, it will be quite easy because they lie next to each other, and whenever you optimize with DMRG, at one point you're going to optimize this to side object. And then you're going to get the optimal possible correlation between these two, and if it has a large weight in your wave function you're targeting, it will in fact also be kept when you decompose it. But when you want to correlate this orbital with that orbital, you might encounter a problem because if this one wants to talk to that one, the communication needs to happen to all the virtual bonds. And if that kind of correlation is important and has a large weight in the ground state wave function, it might be that you just get stuck in a local minimum and it's never well represented. So perhaps related to that, a little trick which you can do, if you look at this, even if you don't, let's say you do this and it's a very hard to converge wave function, just do one sweep at, let's say, bond dimension 4000. Maybe you can pick up this difficult correlation between four lying orbitals. Your wave function is far from converged at that bond dimension, but it doesn't matter because immediately afterwards you can go back to 2500 and then continue. And that's also related to this picture in the sense that if you come in high and once you have a good wave function, you stay low in energy. Okay. Another important property is size consistency. Is the DMRG size consistent? Yes, but you need to be smart about it in the sense that whenever you have two subsystems, A and B, which are non-interacting in the sense that your Hamiltonian is just the sum of a part which acts only in A plus a part which acts only in B, then you need to first take all orbitals of A and then take all orbitals of B. And if you do that, and if you use the DMRG to optimize the matrix product states, the DMRG will automatically retrieve the wave function which factorizes so that the energy is additively separable. If you are not that smart and you take an orbital of A, an orbital of B, an orbital of A, an orbital of B, and so on, then DMRG is of course not size consistent. Last exercise of today. It's a exercise which is in general true for variational optimizations. Hand-wavingly said, it's that for variational wave functions, your energy converges quadratically in the wave function error. What does it mean? Well, suppose you have optimized a matrix product state, which lies quite close to the true ground state, and this is just junk which is orthogonal to the true ground state. And all three wave functions are themselves normalized. Then you can show that the 2 norm of your matrix product state difference with the true ground state scales as epsilon, while the energy difference of the variational matrix product state energy with the true ground state energy goes as the square of epsilon times a factor.
Always one.
Okay. So some people have found the solution. It's just a matter of doing a little bit of pencil and paper work in algebra. The importance of this thing, of this property, is that during DMRG sweeps, you monitor energy convergence and not wave function convergence. So at one point you'll say, my energy is converged until 10 to the minus 6, until microhartree, but that implies that doesn't necessarily imply that your wave function is also really, really well converged. So you need to be careful with that, and you need to keep it in mind. Okay. So as said, DMRG depends on the choice of orbitals and how you order them. And because you can think of the auxiliary dimension as a communication channel for correlations, it's important to place correlated orbitals close to each other. There is, of course, one type of system for which DMRG works extremely well, and those are one-dimensional systems. In the sense that if you have the Hubbard model, or if you would have the pi system of a polyane, if you use localized orbitals for the pi system, you automatically have a one-dimensional ordering associated in your molecule and in your, which is also present in your matrix product state wave function. It turns out that if you use it, you can indeed get away with a very small bond dimension. So the statement is that if you have an infinite matrix product state with a finite virtual dimension, then all correlation functions in the end have to decay exponentially. So you cannot have any phase transitions or algebraically decaying correlation functions. So for us, the consequence is indeed that strongly correlated orbitals should be placed adjacent for elongated molecules such as polyenes, or if you, for example, have porphyrin or anything which has a decent size, or the Semon complex, or anything like that, you want to use localized orbitals. And you want to somehow order them according to the topology of the molecule. When you have very small compact molecules, preferably also with some point group symmetry, it makes sense to exploit the point group symmetry, and the optimal ordering then turns out to be to keep orbitals of the same irreducible representation together, for example, sigma bonding orbitals in a dimer, but to place irreducible representations of bonding, anti-bonding type next to each other. So this is just for a polyene, doesn't really matter which details are here, but if you look at the molecular versus localized orbitals, this is energy convergence versus bond dimension. You see that things converge very, very quick on localized basis and orders of magnitude slower in the canonical basis. So the localized basis, you just have pi electrons on each carbon atom. The molecular basis, you have these signs standing on the entire molecule. Here, the nitrogen dimer is shown near equilibrium. You get less benefit than with these one-dimensional systems, but you still get benefit when you reorder the irreducible representations so that they are of bonding, anti-bonding type. Yes.
Just out of curiosity, the exponentially scaling relation functions, how can you prove that? Is it a trick or is it just straightforward?
It is straightforward. It is, it literally flows out of...
using the structure of the wave function.
Yes. So I can give you the paper this afternoon if you want to look at it. It's Bruno Nachterhale, Thomas.
Okay.
So symmetry, before I talk a little bit about the code you'll use this afternoon, I'll briefly mention how you can exploit symmetry in matrix product states. The discussion today started with putting all symmetry constraints in your full CI coefficient tensor, and then factorizing this coefficient tensor into matrix product state tensors. You can also impose symmetry in the whole DMRG algorithm, and the way you do it is twofold. You do it on the matrix product state, and you do it on the operators of the Hamiltonian. Symmetry in the matrix product state, just as before, we just decomposed this full CI tensor into MPS tensors. You can think about the coefficient tensor of configuration state functions, and when you decompose that object, you would get symmetry adapted matrix product states. That's one way of looking at it. The other way of looking at it is the one which I'll discuss now, and I'll do it for SU2 spin, U1 particle number, and P point group symmetry, where I'll just discuss the abelian point groups with real valued character tables. One of the ideas behind matrix product states is that it's a renormalization group flow to go from one renormalized basis, add an orbital, and go to another renormalized basis. Now, when both your incoming renormalized basis, your local orbital basis, are represented in states with the correct symmetry, you can just recouple your basis states which are outgoing, and it then turns out that you can use the Wigner-Eckert theorem on your matrix product state tensors to factorize them into Clebsch-Gordon coefficients of the groups you use and reduced tensors. So you just write all auxiliary and physical basis in terms of the correct symmetry labels, and then you can factorize in SU2, U1, and the point group Clebsch-Gordons, and you end up with a reduced object. Now, this is nice because, first of all, whenever one of the Clebsch-Gordon coefficients is 0, You don't need to allocate any memory for it. You don't need to perform contractions over the common auxiliary indices. So you introduce block sparsity. The second nice thing about it is that you'll work only with the reduced tensors, in which you have one basis state which represents an entire multiplet here. And the multiplet arises by this SU2 Clebsch-Gordon coefficient. So this compresses information for non-singlet basis states. And of course, the obvious benefit when you use symmetry and you want to look at states in different symmetry sectors, it's just ground state calculations instead of excited state calculations. On this slide, I'll show an example of information compression with, for a one-dimensional Hubbard model. So you just have nearest neighbor hopping and on-site repulsion. We're in the strongly correlated regime. And two colors are shown here on a plot where you have energy convergence versus a monotonically increasing function of the bond dimension. So this just means if you go in that direction, your bond dimension also increases. For the two lines, there's one without symmetry and one with symmetry. The one with symmetry, the bond dimension which is used here is the reduced bond dimension, which means the one of the reduced MPS tensors. So these are also matrices when you fix the orbital occupation, but these matrices are smaller than those matrices because you have here the Clebsch-Gordon coefficient, which goes from a one basis state per multiplet to the entire multiplet here. And the way you have to interpret this plot is, say I have a certain virtual dimension here, and I have a certain energy convergence here, then this corresponds to the virtual dimension of the reduced tensor, which was the T tensor on the previous slide. If you look at the entire multiplet, then you have to go horizontally to here and then back down. This represents that total virtual dimension. But as you know, matrix-matrix multiplications go as linear dimension cube, so you have an actual real benefit in your computations as well. I've said before I started to talk about symmetry that there are two aspects. One is you introduce symmetry in your matrix product state. The other one is you introduce symmetry in the operators that you raise in the Hamiltonian. And the way you do it is on the level of the second quantized operator. So you can, with the proper phase vectors, rewrite your creation and annihilation operators into new creation and annihilation operators, which transform according to particular rows of particular EAPs. So you can also use the Wigner-Eckert theorem for these second quantized operators. And so you end up with a network of reduced MPS tensors, reduced operators, and the whole set of Clebsch-Gordon coefficients. And this whole set of Clebsch-Gordon coefficients don't really arise in the code, because you can pre-contract over all these Clebsch-Gordon coefficients and end up with Wigner 6J and 9J symbols. Yeah.
So spin is one. So the labels are, maybe if you could go to slide back when you defined the so the physical labels, there are S, S, Z, N, and I.
Okay, so
the spin is either 0 or 1/2.
So for the physical basis states, you have indeed, so you have four possible orbital occupations. You have empty, you have an up, a down, or doubly occupied. The empty and the doubly occupied correspond to spin 0. The empty, of course, to particle number 0, the doubly occupied to particle number 2, obviously. And both of them also have a trivial point group irrep. It's only the singly occupied state, which is interesting. There you have spin 1/2, spin projection up or down, depending on which of the two occupations you have. Particle number is obviously 1, and the point group irrep is the point group irrep of your orbital.
Of the orbital itself.
Of the orbital itself, yes.
But then you also have virtual point group.
Yeah. So you again have spin projection, particle number, point group, and just an index which counts because you have many basis states of a certain symmetry.
But given an orbital, the point group is fixed, right? So there's no...
Yes. So the way you have to interpret it is you start on the left with the trivial point group, no particles, no spin, trivial. And then you add an orbital, and this orbital can have different occupations, and it can go to various newly normalized basis states, and these newly normalized basis states can have different symmetries, and then you can add in a second. And then the way it works is you sort of have this tree. You start from the trivial symmetry, then you branch in the middle towards all kinds of symmetries which you can have, and on the right end you want to have the symmetry which you target. So the spin you target, particle number you target, and the point group irrep you target. But I mean, for practical calculations, this is not really important.
But it allows you to get rid of a lot of, yeah, I mean, it's to reduce the bond dimension there again, right?
Yeah, indeed. Okay, then I'll going to talk a little bit about the code we're going to use this afternoon. And then just before we start this afternoon, I'll give the last part of the presentation, which is just 5 slides on DMRG SCF and DMRG cos-2. So the code name is ChemPS2, which stands for Chemical Matrix Product States Program 2. There's a 2 because I programmed it once and did an awful job at it. I needed to redo it. The symmetry groups which are exploited are the ones I've talked about before, so spin, particle number, and the abelian point groups with real value character table. It's fully coded in C++ 98, but there's also a Python interface. There's also just a binary, so you can read in input files, and that's actually what we're going to do this afternoon. It's released under the GNU General Public License version 2. You can just get it from GitHub. In fact, it's quite good to note this link here because it also provides access to the hands-on tutorial for this afternoon. There's a hybrid parallelization with the message passing interface and OpenMP, so both for shared and distributed memory architectures. And by now, the latest version you should be able to just get on Debian or Red Hat based systems quite easily. And if you want to know more about this particular code, you can read these references. They are also available if you go to this link. So scaling of the CPU time, I've said that it goes as follows. You have a factor d squared and a factor d cubed. This comes from matrix-matrix multiplications. This comes from the construction of the renormalized operators. And it might be interesting to see what is actually dominant and how we can interpret it. For that, I want to increase the number of spatial orbitals, but of course you don't want the actual system to change. So the go-to system in chemistry are then polyenes, where you can just keep on adding bits and pieces and your system doesn't really change. If you do so on one core on a modern day computer, you get the following scaling of the CPU time with the number of orbitals for 2 values of the reduced virtual dimension, and you get a factor which is somewhere between 3 and 4, which is something you hope to see. The next question you can ask is, well, if the bond dimension goes up, you want the scaling with L to go down, right? But this is not really what you observe here. As you go up in virtual dimension, your CPU time, your scaling with L, also goes a little bit up. And the answer is, well, this scaling here has been constructed under the assumption that you don't use block sparsity, this information compression, or point group symmetry, or whatever. And if you take all the other things into account, you will get a quite messy scaling. But still, it's good to see that if you look at the scaling with CPU time, you get a power in the number of orbitals which you would like to see more or less. Typical resources. Again, our example of the nitrogen dimer, double zeta bases near equilibrium. You've done everything right for the orbitals, so you group them per IRAP, bonding and anti-bonding IRAPs together, and you work on one modern day node. And you increase the reduced virtual dimension from 1000 to 2500, which is something realistic to do. The wall time per sweep goes from less to 1 minute to a little bit above 6 minutes. So that's reasonably negligible, and for that you already have a quasi-converged DMRG energy. Now when you go from 28 orbitals to a larger system where you have 41 orbitals, H2O in a obscure triple zeta basis, which is dubbed Rose-Ano double zeta basis, also near equilibrium. I studied the system because Garner Chan did so before. And you also work on the modern day node, and you go from 1000 to 4000. The CPU time, the wall time, these are wall times and CPU times. The wall time is already quite a bit larger, and you go from 7 minutes to a couple of hours, 3 hours. But for that you also already have a fully converged energy. And this is also all on one single modern day node. This slide is about the hybrid parallelization. How does it work? I use OpenMP for the symmetry blocks in the virtual bonds. And I use MPI to distribute over complementary and regular renormalized operator pairs. The system is the water molecule from the previous slide, and the timings here are wall times per sweep in seconds. The left plot is for one single node, and here it depends. Up until 16 it's one single node, and above 16 it are multiple nodes. On the y-axis you have the speed up. So if you go from 1 core to 2 cores, you want the calculation to go double as fast. And if you're below double as fast, that's the lack of speed up. So this is actually 1 over time you take in your calculation roughly. So if you look on a single node and you compare OpenMP with MPI, you see that OpenMP wins, which is good because that means that you can optimally use OpenMP on a single node, while if you go to multiple nodes you have to use MPI, so it's sort of the natural thing to do. I've also compared for exactly the same computational parameters with the block DMRG code, and back then they were a little bit slower. When you then go to multiple nodes, so the red squares here are just the red squares from here. From 16 onwards you go to multiple nodes, you can see that you can extend the speed up somewhat more. You can also get to about 1 minute per sweep for that calculation. The the reason why this is possible is because the two parallelization strategies, OpenMP and MPI, are over complementary for loops. So they parallelize different things, and you can switch off on one and not use the other, and you'll see a speed up, and you can do the other thing, you can switch on the other and not the first one. And they are multiplicative speed ups. So if you use 4 MPI processes only, and you use 4 OpenMP processes only, and you use 16 cores, of which 4 MPI processes and 4 OpenMP threads, you can literally multiply the speed up. Okay, what can you get out of CampES2? Last slide before lunch. I can handle excited states next to ground states. The way I do it is by climbing the ladder. So in a certain symmetry sector, I calculate the ground state. Once I have the ground state, you can project the ground state out in this way. You have your original Hamiltonian, and you add cat bra ground state, and then you add a prefactor here. And as long as this prefactor is larger than the gap between the ground state and your first excited state, if you look at your leveling of your system, you pull the ground state above the first excited state. So the ground state of this Hamiltonian would then be the first excited state. I also can get out magnitudes of full CI coefficients. So people have asked me to implement it, and I'm actually against it. Because if you want a magnitude of a particular full CI coefficient, I take my reduced MPS tensors, I have to multiply them with the Clebsch-Gordon coefficients, and I then have to contract the whole network to get one single full CI coefficient out. It goes fast if you want 1 or 10 or 100 full CI coefficients, but if you want actually a large amount of them, it's just a tremendously bad thing to do. So a better way to look at the electronic structure is to look at correlation functions of all sorts. You have single point correlation functions, which would be orbital occupation numbers or single orbital entropies. You also have 2-point correlation functions, which are shown here. The spin SC correlation function, your spin flip correlation function, density correlation function, and singlet diradical correlation function, as well as the 2 orbital mutual information are available. Maybe in the future 3-point correlation functions will be included, I don't know. But it's nice to use correlation functions to look at the electronic structure instead of magnitudes of full CI coefficients, mainly for a CPU time reason. Also included in the code is DMRG SCF and DMRG COSPT2. And for DMRG SCF, you need the exact 2-particle reduced density matrix. For DMRG COSPT2, you also need the exact 3- and 4-particle reduced density matrix. And how the algorithms work, more or less, and how I get the 4 RDM out, I will start with that this afternoon. So, as said before, active space non-consistent field method. You partition your orbital space in 3 parts. There are occupied, active, and virtual orbitals. And you solve the Hamiltonian in your active space exactly. We'll do it with DMRG. I know of 2 other COS-SCF style methods. One is with full CI QMC, and the other one is with the variational optimization of the 2DM by Eugène de Prince. The way it works in CampES2 is with a 2-step code, which means that you do separately a DMRG calculation to get the electronic structure, and then wonder if I rotate my orbitals, can I lower my energy? Then you rotate the orbitals, and then you go back to a DMRG calculation, but you do them separately. There's also a so-called one-step algorithm by Werner and Knowles with full CI, where you intertwine the full CI coefficient changes and the orbital rotations. But that's not the case. So it's a two-step algorithm in Siegbahn's original spirit. So you write the orbital rotation in terms of the exponential of an anti-symmetric matrix, in which you allow the occupied active, occupied virtual, and active virtual blocks to rotate. You express the energy for a given active space DMRG solution up to the second order in X. And in order to compute the gradient and the Hessian, you need up to the 2-particle reduced density matrix in the active space, and the 2 RDM in DMRG comes at completely negligible cost. So in scaling, it's as expensive as a DMRG calculation, but in practice, it's less than 1% of the time you spend on the actual optimization. So you compute the gradient and the Hessian, and then you can do a Newton-Raphson optimization or an augmented Hessian Newton-Raphson optimization. For COS-PT2, you need to know 2 things before I can start with the discussion. One is the generalized Fock operator, and the second thing you need to know is a specific partitioning of the Hilbert space based on your CASA-CF solution. So the generalized Fock operator is a 1-particle operator. The E operator here is just a spin-summed 1-particle excitation operator. The matrix elements are given as follows, where you have here a 1-particle density matrix, and if you would fill in the 1-particle density matrix of a Hartree-Fock wave function, you would get the Fock operator of that Hartree-Fock wave function. So it's a generalization of that concept for multi-reference theories. This thing is symmetric, and it's block diagonal in the orbital ERAPs of orbitals P and Q. The partitioning of the Hilbert space goes as follows. You have 4 parts: V0, Vk, VSD, and the rest. V0 contains 1 wave function, that's your CASA-CF optimized wave function. Vk contains all active space excitations on top of your CASA-CF wave function, which are orthogonal to that wave function. So Vk consists of all wave functions which have the same core or occupied orbitals and the same virtual or secondary orbitals, but which the active space solution can be anything orthogonal to CASA-CF. VSD is then all single and double particle excitations on top of your CASA-CF solution, which are again orthogonal to V0 and Vk. And then if you partition, if you label your indices with Ij for core, AB for virtual, and TUV for active, you have this set of excitations which you quite often encounter. And then you have VTQ, which is just the remainder of your Hilbert space. Now, COS-PT2 is in essence just Rayleigh-Schrödinger perturbation theory with a particular choice for your 0th order Hamiltonian, and the 0th order Hamiltonian is given here. So you have the generalized Fock operator, which is sandwiched each time between projectors onto the space V0, Vk, VSD, and the remainder. It's then quite easy to see that the first order wave function consists of a linear combination over VSD. PQRS, those are the ones on the previous slide from the excitations H to A to H. You can write the wave function as follows by absorbing these spin-sum single particle excitation operators in the indices of the wave function. You can then find these coefficients by solving the following linear equation, and the whole setup of a COSPT2 code is in essence to construct all objects which are needed to solve this thing by sparse iterative minimization. You have here the Fock operator minus your zeroth order energy, and the zeroth order energy is multiplied with the overlap matrix. It's block diagonal in the different excitation types, and I personally choose to diagonalize this overlap matrix and remove it completely. This has one important consequence. If you want to do the cumulant approximation, I will talk about in a second, it's a really bad idea. But I diagonalize and remove the overlap matrix in order to solve this equation, and I solve it with the Davidson algorithm. There's one thing, and then another thing. Your zeroth order Hamiltonian contains projectors, and it's not just the Fock operator, although just the Fock operator appears here in the linear equation. As a consequence, your CF wave function is not a true eigenstate of the generalized Fock operator, and therefore intruder states can appear in the sense that energy differences, Fock operator minus your zeroth order energy, can become very small or even negative, which is of course undesired, and therefore you can add a certain shift to your Fock operator, which has the following form. It's called the ionization potential and electron affinity shift, and it's somewhat the standard shift which has been introduced to mitigate these intruder state problems. So if you encounter problems, play around a bit with that parameter.
Please do not say that. People should not play with that parameter to avoid intruder state problems. They should use the imaginary shifts for that.
Okay.
Because the IPS shift has a very large consequence on relative energies of different spin states. So it really changes your results.
Yes, we'll in fact see that this afternoon, that it has an important consequence.
Yeah, so, but you can avoid that by not changing it. It's 0.25 in COSPT2.
That's true, except when you want to consider transition metal containing systems, then people advise to sometimes take 0.5, and it is a somewhat completely arbitrary shift which has been introduced.
Yeah, but it was not introduced to avoid intruder states.
Okay.
It was introduced to avoid problems with spin set energetics.
Okay.
The imaginary shift was introduced to avoid intruder states. So that should be used for that purpose.
Okay. So I'm sorry, you should use the imaginary shift to avoid intruder state problems. I still don't understand. One thing which you need to do internally contracted COSPT2, which is the variant I have been talking about, is you need to contract the generalized Fock matrix with the 4-particle reduced density matrix of your active space. And that is something really, really costly, in the sense that if you do full CI and you want to do the conventional CASA-CF calculations or COSPT2 calculations, CASA-CF you can still do with 16 electrons in 16 orbitals or 18 electrons in 18 orbitals, but what really, really kills you is the calculation of your 4 RDM as your active space becomes larger and larger. Just because you have number of orbitals to the power 8 an amount of doubles which you need to handle. And that's just, well, it goes as the power 8. It just goes super quickly. And from a certain point onwards, you actually don't want to think about it anymore. So one way to handle it is to loop over S and Z and calculate the corresponding contributions separately and then add them each time to a 3RDM-like object, which you then can keep in memory or on disk. The way I do it is the Fock matrix is symmetric and it's diagonal in the IREPs of orbitals S and Z. So I construct excited wave functions of this type, where you have your CASA-CF solution, you multiply it with a factor beta, and then you add a symmetrized single particle excitation with a prefactor alpha. Now S and Z both have the same IREP and they both lie in the active space. This is a wave function with exactly the same symmetry as psi naught. And if psi naught is a matrix product state, you can also quite easily decompose this guy again into a matrix product state at virtually negligible cost as compared to the 3RDM calculation. So I do so, and then I calculate the 3RDM of such an excited wave function, which can then be used to obtain the symmetrized sum of 4 RDM elements corresponding to S and Z with this equation. So it's just my way of handling the 4 RDM in MPS2. One thing I should also mention is if you want to calculate the 4 RDM in my way, you if you want to use the full 4-particle reduced density matrix in a specific orbital basis, by which I mean a orbital basis which you choose, for example a localized orbital basis if you have an extended system, then you need the 3-particle reduced density matrix of order number of orbitals squared excited wave functions. And that's quite an amount. You always need to wonder what the trade-off is between actually using a localized orbital basis and using a special orbital basis. Sometimes for one-dimensional systems such as polyenes or for extended systems such as porphyrin, I think that it makes sense to use a localized basis because it reduces the reduced virtual dimension so much that it's still cheaper to use a localized basis with a small bond dimension and calculate many 3RDMs of excited wave functions instead of calculating less 3RDMs but with a large reduced virtual dimension. So how can you calculate less 3RDMs? You can do so by working in a pseudo-canonical orbital basis which diagonalizes this Fock matrix. Then you only need a number of excited wave functions which scales as the number of orbitals, active space orbitals. So that makes sense when the point group is high and the molecule is compact. Let's think, let's say transition metal dimers or something like that. It doesn't really matter whether you use the pseudo-canonical orbital basis or Hartree Fock or something which comes out of CASA-CF, because typically you will only have 3-ish orbitals per IREP. So if you rotate them, you're going to block them anyway together. Your entanglement doesn't change that much. So it really makes sense to rotate to a pseudo-canonical orbital basis. If you would do that for polyenes, I've shown you the plot on the bottom left a few slides ago. If you compare canonical versus localized energy convergence, you have at least 2 orders of magnitude faster convergence with localized orbitals than with canonical orbitals. So you shouldn't use canonical orbitals for those systems. There's a third thing which you can do. I have never played with it. That's you can approximate your 4-particle reduced density matrix, and instead of taking the exact 4 RDM of your active space, you can write it down in terms of cumulants. And cumulants is a sort of concept. You first try to build your 4 RDM in a factorized way, in the sense that you try to reconstruct it from a 3 RDM and a 1 RDM or 2 RDMs, and you take all these possible combinations into account. When you write it down that way, there is a 4-particle correlation which is lacking, because you've approximated your 4 RDM up to that point as the product of a 1-particle and a 3-particle correlation, or the product of a 2-particle and a 2-particle correlation. There is an irreducible 4-particle correlation part in your wave function typically. And by throwing that out, you arrive at the so-called cumulant approximation of the 4-particle reduced density matrix based on the 3-particle reduced density matrix. The big advantage: for this guy, you need order L squared 3 RDMs. Here you need order L 3 RDMs. Here you only need 1 3 RDM, the one from the CASACF solution. But your convergence becomes even worse. But as said, I have never played with it, but people have described it in the literature, and Kwon has studied it. So I would advise you to ask him. I don't really have an idea about it. Also, I've mentioned 2 examples here: one-dimensional systems, polyenes, and dimers. And not all molecules are dimers or one-dimensional systems. For example, you have porphyrin. My guess would be that you want to use a localized basis for it, but then you have many in-between examples. You really don't know where should I use a localized basis or a pseudo-canonical basis, and what virtual dimension will correspond by a non-optimal basis choice. I have no idea. Just try it.
Just because when you talk about local orbitals, you mean atomic-like orbitals, or because there are many ways to localize orbitals, so it's not necessarily.
Typically, the way you localize isn't super important in my experience. I just mean in a general concept. So if you have localized orbitals, they take in a small portion of the whole region your molecule spans, and they will have a limited amount of neighbors because of that fact, if you have an extended molecule. While if you have natural orbitals or pseudo-canonical orbitals in an extended molecule, all these orbitals are typically extended as well, which means that they are correlated up to a high degree with all other orbitals.
So, and for instance, let's say that for the polyene, I have local orbitals but that extend over 2 centers. Would that be suitable or not? Or
so could you repeat your question, because I didn't fully get it?
So for the polyene, your local orbitals, I suppose, are localized on one side, so on one
carbon atom
of the chain. Let's say I have local orbitals but that extend over 2 centers.
That's fine. I mean, you probably need a tiny bit larger virtual dimension, but in the examples I've shown, your polyene in a fully localized basis is typically already converged for 1 dimension 100. And when we're talking about 1 dimensions of 100, 200, 500, that's free, so to speak. I mean, it doesn't really cost that much.
Yeah, so then when you lose on the orbitals, then you have to recover it on the wave function. Yeah, so I suppose.
Yes, and sometimes so the idea for an extended system to use localized orbitals is to make them correlated to only a few other orbitals, and then sometimes you can order them so that there is no long distance talking, so to speak.
Yeah. Okay.
For some molecules, there's never a good choice. Let's say if you have a small dimer, I mean, whenever you try to rotate, every orbital is near every other orbital. There's also no unique answer to this question. It's something you have to try out. And even if you have a dimer and you think you have an answer for a certain bond length, if you go to other bond lengths, there might be another optimal solution. So, I can only say that the idea behind using localized orbitals is that they don't touch many other orbitals. So. Okay. Then one last slide, and then we're actually done. You need to compute the 4-particle reduced density matrix for COSPT2. I've talked about a convergence scheme a while back where you increase the virtual dimension up to a certain level with noise, and then you decrease the virtual dimension again without noise in order to make an energy extrapolation. Well, you don't want to decrease the virtual dimension anymore because you want to have an as accurate wave function as possible to compute the 4-RDM of. So in DMRG SCF and DMRG COSPT2, you only ever go towards bigger values of the virtual dimension. And second thing is your accuracy of the wave function, and also the reproducibility, in the sense that if you start the calculation and you get a certain energy and you redo the calculation and you get the same energy and you look at the wave function overlap, it can even significantly deviate from 1, just because of the hand waving thing I've said, that your wave function, your energy converges quadratically in the wave function error. So one thing you can do to get consistently the same wave function, the DMRG wave function, for each calculation is to make your local optimization really converged. And in order to do that, you need to make the tolerance for the Davidson residual norm very small, so that your two-side object at each DMRG calculation and at each step in your DMRG calculation is exactly the same, so you get exactly the same MPS at each calculation. So that's a parameter which you'll encounter this afternoon in the hands-on session. And typically you start with a small bond dimension, you go towards larger bond dimension, then you are going to, at the largest bond dimension, also take a small Davidson residual norm tolerance. So I'm going to go back to this slide in a second. I first want to thank you guys for listening, and money and computer time. This is the Center for Molecular Modeling, and Dimitri, who's also in the audience, was my supervisor for my PhD thesis, and yeah, he would be the second most important guy in the CampES2 project. And for this afternoon, you can play around with CampES2, and for that you can just go to this website and follow the instructions from beginning to end. And if you encounter any problems or you have questions, you can ask me, or if there are computer questions, you can ask White. And if you encounter intruder state problems, unless they are related, unless you want to calculate a correct singlet triplet gap, you should fix them with imaginary double shifts.